In today's lesson, we're going to talk about what happens when direct substitution is not a feasible option for solving a limit. We're going to talk about the most common scenario with that, and we're also going to talk about one of the techniques that is used when you get this situation. So if we let C be a real number, and remember in this textbook C is normally being used in this limit chapter as being the x value that x is approaching closer and closer to for your limits. So we're letting C be that real number, and we're saying that this is f of x, but it's also could be g of x except for at that particular point. Everywhere else, g of x and f of x are the same function. So we're saying it's in an open interval containing C. If the limit of g of x as x approaches C exists, so if that exists, then the limit of f of x also exists, and the two are equal to each other. So what this means is that if you can, let's say you have one of these with an open circle and the other one with a closed circle, then the limit for both of these functions would be the same. So if you could simplify, let's say if the one with the open circle is f of x, if you could simplify that into a g of x, where it's the same except for at that point, then whatever the limit of g of x is, it would also be for f of x. For example, if you look at this problem, the limit as x approaches -4 of the quantity in the numerator x plus 4 times the natural log of x plus 6 divided by x squared minus 16. Now over on the right is a very rough sketch of this, and if right here, if I let the x go in intervals of 2, this is -4. So I do have an open circle here, because you could probably figure out that if you put a -4 here, -4 times -4 is 16, 16 minus 16 is 0, so you have that problem of it being undefined. But notice that everywhere else it seems to be defined except for at +4. But when you put +4 is not defined there, we're not really worried about it. We are worried about it at -4. So -4, you do have graphically a limit that exists. At +4, if I were to ask you that, it would be does not exist, and that could be a common error that students have. Okay, well, notice that you can factor x squared minus 16. X squared minus 16 is a difference of two squares. It breaks down into x plus 4 times the quantity x minus 4. Now what's very unique about this situation is that there is an x plus 4 in the numerator. So for that reason, I could strike this out. Now normally in your algebra class, if you did that, you would have to make a statement where you could simplify it to natural log of x plus 6 divided by x minus 4, and you would have to say where x is not equal to -4, because this is a different function at -4. Everywhere else, these two would be the same function. But at -4, one would be undefined, the other would be defined. But because of the theorem we just looked at above, it doesn't matter, because it's just that one point. The limit from both sides still exists, so when you simplify this, the only difference between the graph would be that would be closed. But now, because it would be closed for this one, you may use direct substitution. And since every other point agrees with the original one, then the limits should be the same. So at this point, I use direct substitution by substituting in the -4, and I get -1/8 natural log of 2. Of course, you can call this negative natural log of 2 divided by 8. Do not take the 2 and 8 and simplify it out. This is just the decimal approximation. I do believe that this rounds to a 7, but remember by AP rules you can just truncate it, and you would have that. Okay. Now, that sort of brings us to one of the techniques where we divide it out. Notice that on that previous problem, since they both had the x plus 4, we divided that out. Now here is another problem that could be used with the dividing out method. Notice that if you put a 0 into delta x, you're going to get an undefined function here. So what I'm thinking is if there's a way that we can mark that out, simplify that out, then we could have a situation where we can find the limit, because every other point would still agree. Now notice we have a different type of thing here. We have delta x. That is different than x. Okay, this is actually sort of preparing you for the next unit. So whenever you substitute this 0 in later on, do not put it in the x. You're just going to put it into delta x. Well, the first thing we need to do is actually expand x plus delta x, that quantity raised to the third. Now you could write this x plus delta x times x plus delta x, multiply it out, and whatever you get for a result there, do it again. But since this is just being raised to a power, one useful technique is to use Pascal's triangle. Now the way Pascal's triangle works, you start with a 1, and notice that I have a 1 on the outside of each level. To get the number here, what you do is you would add the 2 that are above it. Now for 2, you are going to have to just remember that one, because notice there's just one number up here. But to get this 3, 1 plus 2 equals 3. 2 plus 1 equals 3. And then you have 1s on the outside. Put your 1s on the outside. 1 plus 3 equals 4. 3 plus 3 equals 6. 3 plus 1 equals 4. And then you have the 1 on the outside. And you can keep doing this. Well, the number here is sort of giving away the exponent that you are using. So for example, it's also the, let me say this, it's the row as well. This is the first one, this is the second power, this is third power. So for the third power we have the numbers 1, 3, 3, and 1. So what you do is you expand this, just this part. I'm not paying attention to the minus x cubed divided by delta x right now. There will be 4 terms. And you will start by putting each of these numbers to the corresponding term. 1 in the first term, 3 in the second term, 3 in the third term, 1 in the last term. Then what you do, and if you think about when you multiply 2 binomials to get your trinomial, it sort of works this way. It's a little tricky, but notice I have my 1, my 3, and my 1. This is the first term, x. X is showing up in all 4 of these. Now, the first one you start with the 3, whatever this is, and then you work your way down to 0. If there was a number in front of this x, you'd have to put that in there as well. For the delta x, since it's the second term, you start with 0 and you work your way up to whatever this is, and it should work out. Notice there's 4 terms. To go from 0 to 3, you need 4. Now, sometimes people will have a question of, well, what if you switch this around, delta x plus x? Well, as long as you start one of these with the top number working down to 0, the other one with 0 working your way up, since this will always be symmetric with itself, it will always work. You don't have to worry about that. Just keep in mind if that's a minus there, to put the negative with that term, or if you have a negative out here. So I simplify this, and I get, since anything to the 0 power is 1, I get x to the third. And then I work 3x squared delta x plus 3x, and notice since this delta x is being raised to the second, in order to do that, don't go delta squared x squared. This does mean the change in x. It's one value, and the hint is that it's saying delta x is approaching 0. And then I get delta x to the third. The nice thing is, once you have that, then you can change this to its expansion. And notice here, this term simplifies out with this term. X to the third minus x to the third is 0. So please keep that in mind. In fact, that's a very good trick, because keep in mind that you're trying to get this delta x out of the denominator. So when you subtract that out, this is what you have. You have these terms, and I went ahead and I factored out the delta x. Notice there's still one here because this is raised to the second power. I factored one here. This changes down to a 2. Now these two delta x's will simplify out, and you're left with the following. Now since the delta x is gone, and you're allowed to do this because this function agrees with this one in every point except for the one we're testing. Now you can put the 0 into these two terms. So these go away, and you're actually left with an answer of negative 3x squared. Okay? So the previous example was a more standard type of dividing out problem, but this one comes up quite a bit. It's going to be sort of a lead-in for the derivatives unit, which is the next unit.